Good morning and welcome to the ATCO SpaceLab speaker series. My name is Kelsey Stephen. I'm a member of ATCO's transformation team and I'm pleased to be your moderator today. I acknowledge the Indigenous peoples that are traditional custodians of the lands that we are on today. While this is a virtual platform, I will take a moment to reflect on the meaning of place and in doing so recognize the various traditional, ancestral, and unceded lands on which we do our business. I do this to reaffirm my commitment and responsibility in improving relationships between nations and to improve my own understanding of local Indigenous peoples and their cultures. Today's lecture is a one-way webinar. Please ask questions throughout the session using the Q&A button at the top of your screen, and we will get to these questions at the end of the lecture. I will now pass it on to my colleague, Andrea Kleiber-Langen, to introduce our speaker.
Thank you, Kelsey, and welcome to our online audience. We're thrilled to have Dr. Jörn Davidsen join us today, an accomplished professor of physics and Humboldt Research Fellow at the University of Calgary. Professor Davidsen received his PhD with a focus on theoretical physics from the University of Kiel, Germany, and now works in the transdisciplinary field of complexity science. He has worked on applications in neurosciences and earthquakes using tools from statistical physics, network science, and nonlinear dynamics. Today, Professor Davidsen will discuss what complex systems are, why they are interesting, and how we try to describe and understand their emergent characteristics. He will share examples of how we might use these characteristics to understand seismic activity and neural signaling, with potential applications in seismic hazard assessment, earthquake prediction, and tackling brain-related diseases such as Alzheimer's and epilepsy. We are very excited to learn from you, Professor. The floor is yours.
All right, I hope you can see my screen now. If not, let me know. Well, so first of all, thanks so much for the invitation and giving me the opportunity to talk a little bit about the physics of complex systems today. It's really a great pleasure to give an overview of complex system complexity science, including some of the work my students, postdocs, and collaborators and I have done over the years. Before diving into the physics of complex systems, let me start by acknowledging the funding source of research over the years, as well, and most importantly, I would like to introduce also the complexity science group here at the University of Calgary. Our group has been varying between 20 and 30 group members over the last few years, including students, grad students, undergrads, as well as postdocs. And we have 5 faculty members or PIs working across different departments and faculties. These include the Department of Physics and Astronomy, as well as the Department of Computer Sciences and the Cummings School of Medicine here in Calgary. What brings us together as a group is really our broad interest related to complex system complexity science. And we all share a similar background in terms of physics and applied mathematics. So to start with the topic today, physics of complex system, let me start talking a little bit about what a complex system is. And for those of you who are familiar with this or who have a background in, for example, statistical physics or similar fields, right? I apologize. I'll try to keep it very general and try to make sure that hopefully everybody can follow and understand the main concept. So I have very minimal mathematical aspects I'll show today. So what is a complex system? The complex systems typically have shown characteristics, namely the emergence of collective phenomena. So what is that? It's that you have a system that's made up of many components, and these large collection of components, they somehow interact with each other on small scales, and they somehow spontaneously self-organize to exhibit some non-trivial global structures or behaviors at larger scales. So here on these slides, you see examples from atmospheric dynamics. On the left, you have a hurricane, the formation of a hurricane. On the right, you have cloud streets. And what is in these cases, for example, what could be considered the individual components could be the water molecules and somehow arranged to form clouds. In this particular example, the cloud streets, they form these long streets. I'm not sure if some of you might have seen them. When you're in a plane, they do occur. They're not super common, but there the question obviously arises: how does this collective phenomena emerge? Another example I want to focus on is related to synchronization. So here's a little experiment. If you like, you can try at home. If you're a musician and you have metronomes, in this experiment here, they've done is they have two groups of metronomes. They've put them on swings. So if a swing on the left, swing on the right, the two swings are connected with a spring over here. And all you do is you tune the metronomes to exactly the same frequency and then let them run. So what's then going to happen in this specific situation here is, see the group on the left, this group here, is synchronizing. So the clocks go the same way, while the other group, even though they're all identical, they are unsynchronized. So that's an example of a collective phenomena, where in this case it's non-trivial in the sense that some of these oscillators or metronomes or clocks do synchronize while the other ones do not. Another example of collective phenomena I want to talk about is related to birds. Here we have starlings, and they swarm. This is typically in the early morning hours or late in the evenings. The video from the National Geographic, and as you can see, they form many different patterns. New groups join, some groups leave, and this all happens without any clear leader. So that was one of the questions back in the day, right? Is there some birds that lead this group and that lead to this emergent collective phenomena? But it turns out it's pretty much self-organized. So meaning that there's no central unit that organizes this type of behavior. Now let's dive into that a little bit deeper. So if you look at this, we've now established what a collective phenomena is, but let's talk a little bit about what I mean by emergence. So emergent means if you're able to understand and study the motion of individual birds and know how a bird flies, is that enough to understand this collective phenomena? And the statement is that typically that's not the case. So if you know how a bird flies, and you might observe a single bird in isolation, that's not a way to understand how this phenomena arises when many birds go together. And that's what emergence is all about. Namely, that the whole is more than the sum of its parts. And here the key is that the birds interact, and these interactions lead to these formation we just saw, and similarly in the other examples of collective phenomena. So I put down here a little quote from Peter Dodds that summarizes this concept of emergence and how these different aspects go together. That's really this higher level features, the collective phenomena, what this is all about. Now, one can now, based on this, we can define, if you want, at least colloquially, the notion of complex or complex system or complexity science. The one aspect I would like to highlight here is also that many of these complex systems that show these emergence features, the interaction that gives rise to this is in the form of, or can be mathematically looked at as a network. So the pattern of connections really of individual entities, and then they somehow interact, which is described by this type of network, that can give rise. So that's a theme we'll see throughout this talk, recurring multiple times. So if we look specifically at examples, we've already saw the interaction between the birds, but we can generalize this in the sense of looking at social networks where the nodes are humans, for example, or animals. They interact. And again, their interactions can be potentially quantified through direct interactions. Could be a friendship network. It could be an acquaintance network. And one would like to study the behavior of a society as a whole based on that. Another example, again, looking at the quote by Peter at the bottom right, no financial collapse is in the dollar bill. The stock market is another example of a complex system where obviously the different stocks interact, markets go up and down. There's the interaction with the traders. So that's another example here. Throughout my talk and the following, I will mostly focus on two aspects. One is related to geosciences, and they're related to earthquakes specifically. So on the upper left here, you see fault networks as another example of a complex system. So what are fault networks? You have plates, the plate tectonics, they move, and along these lines, you have networks, and they give rise, or that's where most of the earthquakes in nature occur. On a smaller scale, you can consider this as you can have similar phenomena related to what's called rock fracture. When you break a rock or any material for that matter, it will fracture in a certain way, and one can look at the properties. The materials typically that you break are made of many components and interact, and then you break them either through manual interference or potentially through natural processes, like in the case of earthquakes. The other broad set of examples I'll focus on today is related to the brain. So in the lower left, you see an example here of the structure of the human brain. The human brain is made up of the order of 10 to 100 billion neurons. So neurons, we believe, are the smallest units that are relevant for the dynamics of how the brain works. And these are connected by 10 times as many connections. And here in the middle, you see an example of a biological neural network, where you have in the middle, you see one neuron here, one neuron over there. You see how they're connected throughout. And there, again, this type of emergence, you have things like consciousness, free will potentially, and all these things that mechanistically somehow seem to be arising through the interaction of these neurons. So those are obviously fundamental questions. We would like to understand how these things work. But then there's also the question more broadly, right? Why do we care? What's the impact? In the case of earthquakes, it's very clear. Ideally, we would like to be able to predict earthquakes so we can evacuate people on short timescales if a large earthquake is imminent. Unfortunately, that's right now not possible. We're not good at that. We're good at predicting rates of occurrences of earthquakes, such that building codes can be adjusted, but not really in terms of predicting things on short timescales, very precise, and that would warrant evacuation of people. So that's one example why we care about complex systems. Another one, staying in the area of geosciences and earthquakes, is related to industrial operations. So their examples are clean energy sources, such as enhanced geothermal systems. These are cases where you basically inject cold water into the ground. The ground is hot, it heats up the water, and that drives a turbine to generate energy. Unfortunately, this source of clean energy has potentially issues. So there's an example here from South Korea in Pohang 2017, where an operation caused a large earthquake, magnitude 5.5, and had a total economic impact of $300 million at the time. One doesn't have to look that far. Also within Canada, there's the extraction of hydrocarbons through hydraulic fracturing, for example, can lead to earthquakes, and the largest to date was here in Alberta and Red Deer back in 2019 at magnitude 4.7. Other areas where these things happen, or other technologies where earthquakes can be induced, are wastewater injections, which are particularly prevalent in areas of the US, like in Oklahoma. So those are things obviously one wants to understand so we can control it and prevent these things from happening. Other complex systems on the technology side include power grids. So basically how energy is distributed, and one of the main questions is to prevent power outages. Here's an example from about 20 years ago from the East Coast, US and Canada, but even a couple of weeks ago we had this example in Portugal where the whole power grid fails, and one would like to control that and prevent that if possible. And it turns out the interaction between the different power stations and the network itself has all the feature of a complex system and can be mapped to a network, as I mentioned before, and understood in such a way. Sometimes these power outages are also related to natural hazards. So particularly if you think about the sun, the sun is obviously very active. See here on the left, constant ejection of solar flares, and sometimes you get larger events, coronal mass ejection, which we'll see in the video here in a second from NASA. And what happens is that this material and energy released from the sun will, through the solar wind, reach Earth and then interact with our geomagnetic field. On the upside, it will lead then to things like the Northern Lights. On the downsides, if it's very high, these geoelectrical effects can lead to power outages. So we had one back in the, I think, late 80s, early 90s in Quebec that was caused by one of these things. So there, the question is, can we predict space weather and then prepare for these types of things? Another example I would like to focus on is disease spreading or information spreading. So obviously the pandemic is behind us, but obviously you want to understand how does disease spread. So here's an example in the middle slide of an H1N1 outbreak back in 2014, and it's mimicking the infection tree, right? Starting with the initial patient zero, so to speak, and how did it spread, and how to then maybe adopt vaccinations and other measures to control disease outbreaks that are becoming epidemics or pandemics. Similarly, that's why I use the same terminology of spreading in this context. It can be not only the spreading of diseases, but also of information. So on the right-hand side, we have, for example, how fake news were spread during the 2016 American presidential election, showing how that propagated through social media. And on the left, where it's also information spreading, is important is again being back in the brain, right? How do different brain regions interact, and information spreads from one area to the next. So these are all cases where we have shown that why it's important to study complex systems, and this has also been recognized, if you wish, by the Nobel Prize over the last years. So here I've just listed out of the last 10 years, 3 of the Nobel Prize in physics were directly related to complex systems, as you wish. The main one is the one in 2021, which was for groundbreaking contributions to our understanding of complex physical systems. That one was shared between different scientists. One group was working on questions related to the climate system, the other one more on things related to statistical physics, and I'll come back to that a little bit later. The last Nobel Prize last year, 2024, was related to artificial neural networks, and many of the foundational discoveries and inventions that are important in this context are really related to the physics of complex systems, and borrow a lot of the concepts from the things I'm going to talk about today. The last one I want to mention was the 2016 Nobel Prize in Physics, which was related to material sciences, which featured how materials behave under certain circumstances. Well, there's a concept of phase transitions, which I'll come back later in my talk as well. So now, then let me talk a little bit about what does complexity science focus on? What's the goal here? Right? We've seen examples of complex systems. We have now some understanding, also some understanding why they might be important, but what can we do about it? So I want to come back to the previous slide, where the Nobel Prize in 2021 for Giorgio Parisi, which was for a contribution it had made that spanned physical systems from atomic to planetary scales, from the very small scales to the very large scales. And that's indeed one of the main ideas of complexity science. Namely, if you look at these emergent phenomena I've talked about, you want to search for generality across scales and across systems. So this little picture here goes back to the book by Henrik Jensen, Complexity Science, shows on the left-hand side different subject sciences, from the top level sociology going all the way down to individual particles. And the right-hand side, the view of these fields, if you wish, through the lens of complexity science. Namely, that if you look at a given system, it's made up of constituents, and they how interact. And now the question is, are these ways how this interaction work similar between these different scales? So that's what we mean by generality. And complexity science tries to find these generalities, mechanisms of interactions that hold independent of the scale we're at, whether we're at the larger scales, like in this picture here, on the level of societies, or at the smaller scales, at the scale of individual particles. So first of all, then the question arises, is there anything like that, right? If you look at natural systems or the system of interest, complex systems, is there some generality? And so what I want to do next is I want to focus on this generality, namely across scales. So I want to look at systems that are pretty much the same, but they span a large range of scales, from the very largest one to the very smallest ones. So the example I would like to focus on is going back to earthquakes. So if you first focus on the upper left, this is a very simple picture of what happens during an earthquake, a tectonic earthquake. So what you have is you have your fault between the two plates. There's a fault on the left, one on the right, and they move against each other. So that's the plate tectonics. The movement is very slow, here typically of the order of centimeter per year. So what happens is then in this specific picture, right, they move in opposite directions. So you get this stress tension building up along the fault. At some point, the stress becomes so high that the material fractures or starts to slip. And that's the earthquake. And that happens with very high speeds, typically of the order of kilometers per second. And then once an earthquake is over, you basically have an offset. So in this specific example would be 6 meters, which mimics the large earthquake at the beginning of the 20th century in San Francisco. You have a little picture here on the right from those days where they had to mend the fence, so to speak, after this offset. So if this were the complete picture about earthquakes, then you might ask, why can't we predict? Because it seems like stress builds up until we reach a certain strength at which it fails and slips and then resets and carries on like this. So that's this what's called the elastic rebound picture. Turns out the situation, if it were like that, right, then earthquakes would occur periodically. Unfortunately, the real situation is more what's shown here on the bottom page, namely the load is not uniform in time. Sometimes goes a little bit faster, sometimes goes a little bit slower. And then the strength at which an earthquake might occur will also vary over time. The material gets stronger or weaker through all sorts of processes. Now, why is this loading? I said before, it's the tectonics that drives the process. That's correct. But once an earthquake occurs, it induces other earthquakes, the so-called aftershocks. And this is through stress changes. So here's on the right is a very rough picture of how this happens, right? You have a rupture here. The waves propagate and lead to changes elsewhere. And then the stress can either increase or decrease someplace else. So it's not just the tectonic loading, but also internally the redistribution of stress that adds to this. And that's why sometimes the loading is a little bit faster, sometimes a little bit smaller. Now, as I said, I wanted to focus on earthquake as an example to see some generality across different scales. So if we look at the largest earthquakes, the next slide, we have on the right-hand side, we basically have shown somehow how likely it is to observe an earthquake of a given size in different areas, from the Alaska area, South America, Northwest Pacific, and Western Pacific. So on the x-axis, what we show is the size of the earthquake, the magnitude. So that's what most of you are probably familiar with. And on the y-axis, I show the frequency, rather the logarithm of the frequency with which these occur. That means if you go from a number of 2 to 1, it's 10 times less likely to occur, an earthquake to occur of that magnitude, right? So for example, if you look at the Northwest Pacific, earthquake of magnitude 6 occurs, and I think this is annual occurrence, occurs about, this is annual, it might be, no, it's over the whole period, sorry. So this is over about a 30-year period. It occurred about 100 times, while if you look at a magnitude, earthquake of magnitude 7, you see that occurred about 10 times. So that's how you can read these graphs. So physically, however, magnitude is not really the unit you want to use if you want to describe the size of an earthquake. We use it because it's convenient, but the true quantity we're interested in is more like the energy, how much energy is released. And that's roughly what's described by the seismic moment of an earthquake. And the magnitude is just a logarithmic measure of that. So in order to make it more manageable, the numbers, instead of having to talk about really a wide range of numbers, we bring them down to this logarithmic scale. So that's why it seems like earthquake of magnitude 6 or 7, that's not much of a difference, but actually in terms of the energy release is about a factor of 15 difference. So it's huge. So now what do we learn from these distributions here? We see, as I say, we have this logarithmic scale here. So mathematically, that would be an exponential distribution. But then if we take into account that the magnitude is logarithmic measure of the energy released, we really have a distribution of this function. And this is really the only main formula today. Namely, if you're looking at the number of earthquakes above a certain magnitude, that will vary with that magnitude threshold with some power law. So power law means there's some exponent here. So what's the implication? The implication is really there's no typical scale. So earthquakes don't occur, there's no typical size of an earthquake. They occur of all sizes, right? They get less likely the larger they are, but not in a rapid way, right? As we saw here in this example here, magnitude 7, where you had 10 of these and you had 100 of magnitude 6 in this time interval. So these are non-negligible numbers, and it continues like that, and it seems there's no change. So that's an indication that there's no specific scale, which is one of these features I want to follow up with, right? Because we're looking at things that are we want to look for general behaviors in these complex systems that behave the same across different scales. So this is the larger scale. So now let's walk down a little bit. Let's go to earthquakes at a smaller scale. So here if you focus for a second on the right-hand side, we have the same type of distribution we just saw. We have the x-axis, the magnitude, and then shows how often they occurred of that magnitude. So for what type of earthquakes is this? So this is now earthquakes, not the tectonic ones I talked before. These are rather ones that are associated with, let's say, areas like Yellowstone National Park, right, where you have a lot of geothermal activity in the ground, which leads to fluid in the ground propagating, which then in turn lead to earthquakes or so-called earthquake swarms. The example I show here are mostly from California and Nevada, the 3 different areas, which you can find here on the map. And the earthquakes that have been observed in this context are much smaller magnitude than the ones before. Before we looked at magnitude 5 to 9 or something like this. Now here we're in a range magnitudes going between -1 and 5 or 4. And we find the distribution follow exactly the same type of decay, namely is this exponential decay. And the slope, let me quickly go back, which we had here, right? All these slopes of the decay were all characterized by the slope by a value of about 1, 0.92, 0.91, 0.95, 0.95. And we see that's the same as happening here. So that's was discovered originally by Gutenberg and Richter and carries the name the Gutenberg-Richter relation. And we see here that this holds also this scale as a smaller scale, smaller earthquakes, but also if the mechanism is different, whether it's tectonic or fluid induced. We can go even smaller. So here's some data some of my collaborators have collected in South Africa, in deep underground, where they were able to monitor earthquakes in the range from -1 to -4. So these are -4, just for context, right? That's something you would not notice. So it's basically very, very small scale. I'll show you in a second an experiment that gets roughly there, and it's really very, very tiny earthquakes. And there they found, so on the left they show where they found the earthquakes. It's a map where they occurred. On the right, they show again the different ways how to group them together and what their size is, how they change with the magnitude. And again, we find something that's very close to this Gutenberg-Richter relation, namely a decay with this slope of 1 in this semi-logarithmic representation. Now let's go to the lab. Let's make it even smaller. So what do we do in the lab? So if you look at the bottom figure here, it's an example of an experiment. So we do some sort of compression. Typically, we don't compress these toys, but rather rock samples. These rock samples shown on the top here in the schematics of the order of 10 to 15 centimeters in height. And so you compress them, and before they break or fracture, you have a lot of microfractures inside, mini earthquakes, if you wish, which you can measure through acoustic emissions. And there again, you can play the same game. In which size do they come? And it turns out they follow a similar distribution as the other ones. So they have, again, a p-value close to 1. So this is still, you could say, well, okay, we're down to the lab scale. So we're smaller than magnitude -4 in the for tectonic earthquakes. So this is in the range, if I were to convert it to magnitudes, we're probably in the range from -4 to -7 earthquakes, so really tiny. But you can even go smaller than this. This is one experiment that has done that, where they fractured a single crystal. In this case, a sapphire crystal, so it's very, very small. And then again, the fracture process they could measure here through some other technique, through photon counts. I don't want to really get into detail, but it's more about what's the amount of energy released. And it turns out it's the same story. We find again this Gutenberg-Richter relation with a b-value of about 1. So what we've seen here is through different frictional sliding, tectonic, or fracturing processes from the largest scale, right, the largest earthquake we see in magnitude 9 up to the small scales, we find the same features. So that's an example of generality across scales of an emergent phenomenon. So what I want to do next then is I want to broaden this, and I want to now look at across systems. So I said earthquake, the most largely earthquakes we talked about, or fracture if you wish. Now we want to see what can happen if you look at different systems, and is there generality between different systems, not just between scales. So here's what I want to talk about. It goes by the name of crackling noise. So let me start on the left of the slide. Here we see again the earthquake distribution. Again, I think this is for Southern California, if I'm not mistaken, shown again that the probability goes with the size to some power inversely. And on the top, it also shows the energy. And here you can clearly see the difference between the magnitudes in terms of the energy released. Now, these earthquakes, as we discussed, are really discrete events, right? Most of the time, nothing happens, and then an earthquake happens. And these types of discrete earthquakes or discrete, if you want, you can call them crackles, also show up in other systems. That's what we mean by crackling noise. So, for example, if you crumble paper, right, and you can try that at home, you crumble it, that's a process where you'll hear crackles, and these crackles, they come really in, you can very loud ones and ones that are almost silent. So you get a wide range, enormous range of these sizes. That also happens if tomorrow morning, right, at breakfast, right, you have some Rice Krispies, let them soak in milk and just listen to them. You'll hear the same thing. You'll hear tiny crackles, large crackles, spanning a large number of sizes here. Same is true if one magnetizes certain materials. I'll come back to that example later. Or if you go out camping, right, campfire, same thing. These crackles come in all in all sizes. So there are other examples on the slide here. I don't really want to go into detail, but that's the key takeaway here. Now let's focus on one of these examples of crackling noise further. Let's go to the example with the magnets. So what happens here? Again, it's an experiment you can potentially do at home. So you have some material that is not magnetized. You bring a magnet in. So that's what this shows here. So here's the material in blue. It's not magnetic. You bring in a magnet and you magnetize it. So so it's basically turning, if you wish, a paramagnet. For those of you with the physics background, it's turning a paramagnet into a ferromagnet. Now, when this happens, when you magnetize the material, that doesn't happen all at once. It doesn't turn from being non-magnetic to magnetic, but it's a process. And here in the middle, we see how this happens. You can listen to it because it induces once starts magnetizing, inducing a current, so to speak, and you can listen to this and you hear these crackles. And again, they come in all different sizes. And then you can say, okay, well, what is the size distribution? As I said, for all these examples of crackle noise, we have this wide range, but what's their size distribution? And it turns out, and that's shown on the right here, for different materials, etc., that they also obey a distribution very similar to this Gutenberg-Richter relation we talked about. Namely, we have this R-law relation here. And this is a system that's very, very different, right? This has nothing to do with fracture or earthquakes. So this is a good example, together with all the other ones I mentioned, and I don't have time to go into detail and show results for them as well, that all these systems that show this crackling noise share the same features, namely these Gutenberg-Richter-like relation, their size distribution. Okay, so if we take now a step back, right? Complex systems are characterized by emergent phenomena. Complexity science wants to try to understand it, taking advantage of some generality across scales and systems. How exactly are we going to do that? So fortunately in physics, there are a few tools we have to tackle something like this. So one of them goes back to work by Wilson, who got the Nobel Prize in Physics in 1982, who provided an explanation why in certain physical systems, a lot of details of a model do not matter. And these are systems that are characterized by so-called phase transition. And I'll explain in a second what we mean by a phase transition. And the most simplest things you can think of this, a phase transition going from a liquid to a solid, right? Or from a gas to a liquid, that would be a phase transition. And many of these systems at this point of a phase transition show exactly the same behaviors, independent of all the details. So it's very similar to what we just saw. Namely, we had a lot of different systems, different scales that we had, some are similar. And in particular, what Wilson showed is that at these points, these phase transition points, these special points, you also see these Gutenberg-Richter-like distribution of sizes. So the issue here is a little bit, they're twofold, right? One can say, okay, why don't we use that right away? Well, the problem of this picture is that this picture was developed for systems in physics in equilibrium. So those are the systems in thermal equilibrium, there's no dynamics, really. All the systems we've talked about so far do not fall into that category. Instead, there's a lot of dynamics changes over time that are important. There's an energy inflow and outflow typically for all these systems. So the framework does not directly apply, so we have to work a little bit harder to get there. Before I talk about that in more detail, let's follow up a little bit on what do we mean by a phase transition. As I said, one example would be going from a liquid to a gas. But let's take another example that is maybe easier to understand, especially that is very general. So I want to spend a minute or so or two to talk about what's called the branching process. So branching process is very similar to spreading. I talked about disease spreading, and maybe in the context of what's important here, let's take the lens of a spreading process, disease spreading, even though the model we have here is very general, the mathematical model, and applies to many different things. So what's the setup? Well, we look at the following. We have some sort of a generation 0. What's that? That would be if you have a disease outbreak, patient 0. So that's the first person with that disease. So at that level, we have one person, and that person might spread the disease to 3 other people. So it means in the next generation, that's what we call the generation, the next level, he infects, or he or she or they, in this case would be 3. And then these in turn can also affect others. So in this case, for example, this individual over here infects 2, this one nobody, and this one 3, and then it carries on. So in this sense, you can, the spreading process then takes this form of this tree, if you wish, mathematically, right? And that's what's called the branching process. And it turns out what's important if you want to study this, well, one question could be, does this tree ever end, right? Does the disease spreading stop? And that obviously in the pandemic we just went through, that was obviously one of the main questions. And that's at the time, right, this notion of an R value came to play. And R value is really mathematically the important piece. So here in this slide, it's called sigma, and it's really the average number of direct activations. So on average, how many people will be infected by a given individual. So it turns out if that average number is less than 1, then this tree, the spreading tree, will eventually die out with probability 1. It will always die out. At some point, it will just end. Okay, so if it's on the other hand, this value is bigger than 1, then there's a good chance that this spreading will continue forever and the activity will explode or grow in time. And then in between, you have this point, and this is exactly sigma as 1, where it's exactly at the edge between these two. So mathematically, for those of you with mathematical background, that means it will still, the tree will die out with probability 1, but the size of the tree is arbitrarily large, or can become arbitrarily large. So that's what we mean by a phase transition. It's the point between 2 different regimes, right? Said before, it could be liquid and gas, and you're right in the point in between. Or here, the disease really spreads, cannot be controlled in one case, in the other case always dies out, and there's this fine point in between. That's what we mean by a phase transition point, or a critical point, or criticality. Now, if you approach this point, this critical point, as I said, the probability of getting larger and larger trees grows, and one can analyze this, and that's shown here for slightly different but related systems. For percolation, it doesn't really matter too much here. So there's one set of sigma, now we call this P in this case, and when you get closer and closer to the critical value, right, you get larger and larger trees until as I said, at the critical point, at the phase transition point, they can become arbitrarily large, and again, they follow power law, very similar, exactly like in the Gutenberg-Richter relation. So in that sense, this a very simple model of a branching process, which you can study mathematically, can capture all these features we just talked about. Namely, it has it generates these scale-free behavior, these Gutenberg-Richter-like distributions. So if one takes a little bit step further and looks beyond the Gutenberg-Richter relation and takes this as a model of information spreading, for example, or information transition or transfer, one can also show that this being at this critical wall is optimal. And that will become important later when we talk about the branching process as an example or mathematical description of what's happening in the brain and how neurons spread activity, for example. Okay, before diving into the neurons and the human brain, let's quickly come back to the conceptual picture I talked about before, right? The one developed by Wilson, which basically says if you are at this phase transition point in your model or in any other model along a certain line in this simple picture, they will all behave exactly the same way. That's the main statement. If you're a little bit off, it will behave very differently. Now, as I mentioned before, this is really, you need to tune the system to this point, and you have to be in equilibrium, which we're not for the system we talked about. So that's why this notion of self-organized criticality was proposed, namely coming up with the way to propose a mechanism that somehow the system self-organizes to a point that is like a phase transition point that we saw in the simple model, for example. And so that's the idea. In the context of earthquakes, I think we have a very good argument to make that. Namely, it is this very slow driving of the tectonic plates that typically keeps the system at a certain point. Namely, if you think about having a block which you push, if you don't push it hard enough, it's just stuck. It remains stuck because of friction. If you push it hard, at some point it will slide. But if you then stop pushing, it will stop again. And that's exactly the picture we have for the earthquakes right now. Namely, that the tectonic loads at some point will push it and start sliding, and then it will just get stuck again, such that you're always close to this point where it wants to start sliding. That's the conceptual picture. For those of you interested in more detail, you can look at the work by Jim Sethnas and others. I don't want to get too much into that because it gets mathematically very heavy if one wants to explore that a little bit further. So instead, I want to switch now a little bit gears, and I want to talk a little bit about neuronal systems and critical spreading, like in the branching process we just talked about, neuronal systems. So do we have examples? I mentioned it is a model for that, but let's see if that's indeed true and how experiments support that. So here, what I want to show is a little video. So what are we looking at? We have a little culture in a petri dish. It's a culture of nerve cells. So all these bright spots you see here are nerve cells. And you see a little bit of some of the wiring between the nerve cells. So that's basically what our brain is made up of, right? It has all these different nerve cells. They're connected and they communicate. How do they communicate? So each neuron can be in the simplest case in two states. Either it's in a state of quiescence, so it's not doing anything, or it gets active. So how it gets activated? Well, if it gets input from some of the other neurons it's connected to in the form of so-called action potentials or through some biochemical coupling that can activate it. So basically, this is the state, if you look at it from the voltage, you can measure the voltage of the nerve cell. It's in a rest state, and if it gets input, and the input is stronger than a certain threshold, it will activate, and it in turn will send a signal to its neighboring cells. So that's what we see here. So sometimes the cells light up, and that's the experimental technique with which we can measure whether a cell is spiking or not, and then you can see some propagating through the network to some of the other neurons. So that's an experiment done here in Calgary at the lab of Michael Kolikos back in the day. And now, once you have that, right, you can look a little bit more into detail into these patterns. How do they activate these different cells? So on the next slide, what we see is the same movie still, and then on the right are some examples of what type of behaviors you can see. And this, just to be very clear, right, these are nerve cells in a petri dish. So there's no external stimulation. It's really spontaneous activity by the cells, which means one cell spontaneously activates and then spreads. So in that sense, it's similar to the branching process. And what we see on the right now is we have a graph. We have time on the x-axis, and on the y-axis, we have the different neurons. So in the upper one, we have about 1,400 nerve cells we can observe simultaneously. And every time they activate or spike, we put a little dot. So we see in this upper recording experiment, it was very regular in the sense that almost all cells typically fire together in a short time interval and then there's quiescent. Well, in this experiment down here, that wasn't the case. It looks more random. Some neurons seem to be firing faster than others. Now, bringing it back to this idea of spreading and a branching process, I want to focus on the upper case. So why is that? Well, because if neurons happen to activate together in a short time interval, and we know there's no external stimulus in the system, so it's all spontaneous activation, it makes sense to assume that, again, you have this type of spreading, disease-like spreading we talked about in the context of the branching process. So then you can zoom a little bit closer into this. So this is, again, the same thing with time here. If you hear basically the neurons, and you can zoom in into one of these time intervals when they all seem to be spiking together. But if you look at time scale, right, there's a certain order at which this happens. And you can measure and say, okay, how many neurons actually fired? And then you do it for all of these, right? So identify when you have one of these outbreaks, of activity, how large do they get? So it's basically like measuring the size of these trees when we talked about the branching process. And then you do a histogram like for the Gutenberg-Richter earthquake-like distribution, and this is what you find in black. So you see exactly the same thing, namely, you get very large sizes. They span here 2.5 orders of magnitude, right? From activity where only a single neuron fires up to a case where 300 or 400 neurons fire together, and they follow again a distribution not too dissimilar from the Gutenberg-Richter relation we saw for earthquakes before. Okay, so this is on the small scale, the individual neurons. We only saw, so the question then arises, A, how does it translate to cases where with live animals or humans? B, how does it scale to larger scales? Right? We only looked at this a very, very small number of nerve cells, and I told you the human brain has of the order of 10 to 100 billion neurons. So in order to do that, we have to change experimental techniques, because now we can, if we want to look at the whole brain, we cannot really image individual neurons. So what we do instead is, in this case here, we're looking at what's called the mesoscale. So we're looking at the mouse brain. Here's the mouse, or here in the video. We're looking at the left hemisphere of the mouse, and we image the activity. And the activity now is of the level of hundreds of thousands of neurons together with a camera. And we see we have two different cases here. So in this specific case, we had the mouse was anesthetized, I think with a certain drug, and was monitored then the activity right after they got the drug, and then when it woke up, and to see how does the activity change. And if you see, it actually does change quite a bit. Let me just play this again. Particularly when you're anesthetized, very often, at least for this case, you see wave-like activity going through, right? There was a wave front coming through. Here's another one in this case, which does not happen in the awake case. And you can now quantify that again, and you can say, okay, this activity outbursts, which sizes do they come? Again, how large are these spreading trees, if you wish? And what they found is this. So they have 3 different mice. So we just focus on mouse 1. So they have early on, right after they were given the drug, and they see, no, we get characteristic events, namely the distribution somehow is flat. That means a lot of events of these activity are of the same, are equally likely, and they're all pretty much the largest size. And this is because we have these waves coming through. But if then the animal wakes up, we go back to a state that looks very, very similar to this Gutenberg-Richter-like relation, namely we have power law behavior, and we get events of all sizes. There's no typical size anymore. Then you can ask, well, this is for mice. What about humans? And humans, you can do the same. So here it's just a person in an fMRI scanner, resting state. So they're just relaxed, and you can record the brain activity, right? And you see typically activity starts somewhere in some brain region, then spreads to other region, and then it stops, and then another one starts. So again, the same thing as before. And you can again measure the sizes. And what you find here is the same type of scale-free Gutenberg-Richter-like distribution we have seen before. So in the context of the brain or neural system, again, we see that this stuff holds across different scales, but it seems to be requiring that you're awake, right? So if we go back to the last slide, right, I said if you're under aesthetics, that's no longer the case, right? We're no longer there. But if we're awake in a resting state, it seems we are in this type of self-organized critical state. So now let's look at, still in the context of the brain, but let's look at something else to explore it a little bit further. So here we're looking at sleep. So we're looking at mice imaging, again, the cortical surface during sleep, induced sleep. And most of you might know that when humans or animals sleep, it's not just one type of sleep, but there are different sleep phases or sleep stages. One of them is the rapid eye movement phase. Historically, it was always thought that that's you're either in the one sleep stage or the other, right? So you either have in the sleep stage that corresponds to this rapid eye movement, or you're not. Turns out the situation is more complicated, is that some parts of your brain could be based in this rapid eye movement sleep phase, which is very similar to being awake, while other parts of your brain are not. And so here we studied this in the context of mice, and we could see that this transition from REM, rapid eye movement, to non-rapid eye movement sleep is characterized by desynchronization avalanches. So that means you can consider REM as a brain activity that's desynchronized. So similar to the example with the metronomes that we saw earlier, where they all do something differently, while in the normal sleep, the non-rapid eye movement sleep, everything is synchronized, so they do the same thing. And this transition you can show is really like the spreading of activity we saw in this branching process, now in space and time. It has exactly the same characteristics. It has the same Gutenberg-Richter-like behavior in the sizes, and it has exactly the same exponent as we saw as you would find for a standard critical branching process. Okay, so again, so far we've talked about either resting state or sleep. What about behavior? So that obviously becomes important if you want to understand the role of this, if there's any benefit, right? Is there any benefit for the brain to self-organize, to be in a state that is very similar to this critical point or this critical behavior? So what do we know about behavior, and how can we relate that to the neuronal dynamics we saw? So behavior, I have here just a few examples of many different observations. You can see that a lot of animals and humans behave in a certain way that shows features very similar to this Gutenberg-Richter-like distribution. So for example, let's start on the upper right. You have a mouse where people just monitored how long do they run for when they run. And turns out the running event size here, I think they've measured in terms of duration, so in seconds, right? They run from very few steps only to about 1,000 seconds. And it turns out there's no characteristic run event, right? So if it's spontaneously a rodent decides to run, it's not that, well, they always run for 5 minutes or so. No, it can be very short, can be very long. It follows, again, this Gutenberg-Richter-like distribution. The same is true if you're looking at fish. So fish swim, right? How fast do they swim? How do they change their direction, right? Very, very similar story. And then the other example I want to quickly talk about is foraging behavior. So when animals go hunting, how do they do that? And it turns out in most animals, not all of them, but here we have an example of different fish. We have a penguin, and we have turtles, sea turtles here, I believe. They all show very similar features in the sense there's no characteristic or typical scale. So then the question arises, if this is true, we have these features of behavior that shows these Gutenberg-Richter-like features, and we also have something similar on the scale of individual neurons. Do these two things belong together? So what do you need to do? Well, you want to observe both at the same time, the behavior and what's happening at the level of individual neurons. So that's what's an experiment we've done, or was done in the lab of Aaron Gruber here in Alberta at the University of Lethbridge, where they had a mouse on a treadmill tracking the running periods, and then at the same time monitoring the activity in certain brain parts of the neurons. So basically, the experiment can be summarized by the figure at the bottom. So we have this white line at the bottom shows the track speed, how fast the animal's running. So sometimes it's not running at all, it's stationary, then it starts running, sometimes a little bit faster, and slower, and it stops again, and so on and so forth. And then on top of all of this, it's basically all the neurons that were imaged and whether they're active or not. White dot means it's active, black dot means it's not active. And one can, first, what we see is there's certain neurons that when the animal runs, suddenly activate quite a bit. So for example, all these neurons down here, if you follow them in time, whenever it runs, you have a lot of white spots. So that means they get activated. Similarly, you have other neurons, when you run, they shut down. They're no longer active. They're less active. So first of all, the neurons don't all behave the same way. If there's certain behaviors, some of them mimic what's happening with the running in the terms of upregulating, being more active, and others, to the opposite, they downregulate, they're less active. And now you can measure the behavior, namely how long does a mouse typically run for, what's the distribution of that, and then what do all the neurons do, and do we have this information propagation, this neuronal avalanche I talked about before. So typically one will then focus, well, one can take all neurons together, or we can just focus on subgroups, doesn't really matter. And what we found was that we have a coexistence. Both things happen simultaneously at the same time. On the left, we have the length of the running event, so how far did the animal run? And this spans from, again, of the order of less than a centimeter, of the order of a millimeter, up to about 100 centimeters. Over that range, we find everything. There's no typical size. And at the same time, if you look at these neuronal avalanches, right, the spreading of neural activity, it has the same Gutenberg-Richter type of behavior, with the difference that the two groups, right, the ones that are more active during running, while the other ones are less active than running, they behave slightly differently. Namely, one has is less steep than the other one. So now, where are we at with this now? So we have shown that they can coexist, but is there more than coexistence? Can you map them one-to-one? And we have done some preliminary work in this direction, but that's really an active field, not just for us, but for many other groups working on complex systems, especially in the context of neurosciences. Okay, then to wrap things up, I want to come back to the examples of complex systems we have seen today. I hope I've been able to convey to you what complex systems are, why they're interesting, and why it's important to study them. And I want to leave you then with a quote from Peter here that I think conveys the main aspect and the main idea about complex systems. With that, I would like to thank you for your attention. I'm happy to take questions.
Thank you so much, Professor Davidsen, for the wonderful lecture today. We're very grateful that you joined us. We're now going to move into the Q&A portion of today's event. So for everyone joining online, please feel free to ask your questions using the Q&A button, and like the questions that are in there to upvote them, and I'll try to get to as many of them as we can in the time that we have today. I see that we already have a couple of questions in the chat here. The first one comes from Robert. Is it often difficult to decide how small to break down a system to decide what to call the individual components? For example, people, neurons, molecules. How do you decide when to stop?
Well, that's a good question. Thanks, Robert, for that question. The answer is you don't know. So it might depend on the question you ask, on the question you have. As I said, the idea, at least of complex design, very often is to translate from one scale to another. Whether this is already the lowest scale or not, it's not necessarily clear. I mean, the example for in the context of the brain I showed, we believe it's the neurons, but the neurons themselves have their own dynamics, and they're so it's not too obvious. And also sometimes might depend on your measurement technique, right? You might have not seen the smallest constituents. So I think there's, in general, no answer really to that. As a physicist, you would probably want to go as small as possible, but then where do you stop? Do you stop at quarks and gluons, or do you try to go smaller? And is it really important for the questions you want to try to address?
Thank you so much. I had a question as well that I wrote down so I didn't forget. In humans or in other animals with brain damage, do you notice that there's a change in the neuronal behavior that you were describing?
So that's one of the areas we're also interested in looking at, right? Certain diseases in particular. What very often happens in many diseases, it could be, especially depends on the origin. It might depend on the wiring rather, that the wiring is changed. So how they interact, not necessarily how an individual cell behaves. But that really depends on the disease. What we've seen is, for example, if someone has brain damage through an accident, right? Certain parts of the brain get heavily damaged. Sometimes other parts can make up for that and can compensate. So the brain can rewire and reroute to some degree. Other diseases like Alzheimer's, there we know some dynamics on the individual neuronal level that can be affected.
Thank you so much. We have a second question from Robert. Can you use the power law behavior at a small scale to predict emergent behavior at a large scale? For example, could you use neuron patterns to make predictions about the behavior of social networks?
That's a good question. It's challenging. I mean, if truly the system is scale invariant, you would hope that some things would translate. Having said that, right, the connecting the scales is one of the open questions very often. So in the context of neuroscience, for example, people who do studies on the full brain scale, like fMRI, or people who are doing EEG measurements, it's very hard for them to relate that to the individual dynamics of neurons. So there's a disconnect very often even between the communities to talk to one another and see, you measured this, I measured this, how does that go together? The hope is there is some connection, but I think we're not, at least at this point in time, we haven't really established that across all scales. In some scales we can, but not generally.
Thank you so much. We have a question from Carlos. Carlos says, thank you for this interesting talk. In your group, are you also using the wavelet transform as a tool to analyze the different scale-based phenomena that you mentioned? If this is the case, what is the effectiveness of this mathematical tool?
Yeah, thanks for that question. So actually the study I showed were with this REM sleep. That's where we use wavelet analysis. So it depends on the question you have. Sometimes it comes in handy. So there, in the context of the sleep stages, we had to somehow to determine whether a certain brain region is in a state that mimics REM sleep or whether it's in this non-REM sleep. And that you can filter out through the different frequency contributions. And that's where we use the wavelet transform to measure it on sliding time windows, what's going on to relate them. Ultimately, again, it depends on the specific question you ask and what you're interested in, but in some cases, wavelet transform have indeed been very helpful.
Thank you. We have a question from Katya. Katya says, thank you so much from another former CAU student. Very interesting topic for me as a current emergency manager. Are you aware if complex systems have been studied in post-disaster scenarios as well, or just in the context of the hazard itself?
Well, the field, I focus today on the physics of complex system, right? So that's why I focus on the hazard side and things like that. There are a lot of people more on the social sciences side who are interested in that, and they do exactly these types of studies. It's the field itself is pretty broad, and also the notion, I mean, I try to come at it from the physics point of view, right? What I mean by a complex system and complex designs. Other people might take it more broadly. So there's a lot of things that would fit under that. But the aspects you mentioned is certainly one area some colleagues are working on for sure. I think even within the American Geophysical Union, there are people working exactly in that type of area.
Thank you very much. We have a question from James. This is super interesting. Do you find you have enough support to pursue research on complex systems within your disciplinary field? For instance, your investigations bleed across many disciplines and fields, so how do you maintain support for and credibility within any one field, or is this even a problem in your experience?
Yeah, so in our field, well, I guess it depends where you're located. So in the Canadian environment, we have a number of grants these days that try to cross disciplines, targeting transdisciplinary research, multidisciplinary research, or interdisciplinary research. So we have been funded through some of those programs. Other programs are more specific, and again, I think we have been successful in the sense that establishing some reputation both on the geosciences side as well as on the neurosciences side, so we can also go for grants that are specifically in those areas, but then highlighting the transfer of methods and approaches between fields and coming really from complexity sides. But I know in other countries that's more challenging, and depending really on which area or which niche you're in, it can be very challenging.
Thank you very much. We have a question from Syed. In your research and experience, have you encountered many outliers or anomalies? And have you had any such questions or things like that inspired you when you were a child?
Well, I think it depends what you mean by outliers, right? I mean, there are always some interesting features you did not expect. I mean, I think that's the nature of doing research. When you start a research project, very often you have something in mind, some idea, which might or might not work out in the end. And those are then, if you wish, surprise or outliers potentially that then can stimulate other research. So, I mean, we've certainly seen a fair share of unexpected features, either in data or in certain models we studied that have led us on a different trajectory than originally intended. I'm not sure if I did not, so regarding my personal trajectory, I did not plan when I was younger to A, be an academic, or B, working on these fields. So this things has evolved over time. So I didn't really have the preconception already early on what I would be doing or where I would be going. So it was really a more winding road compared to others, maybe.
Great, thank you very much. We have a similar kind of follow-up question from Alita. What initially inspired you to begin work in this particular field? Can you share a bit about your journey?
Yeah, so I think, as mentioned in the introduction, I started out in physics and theoretical physics, and I was interested in features and aspects that also you could observe in nature. So that was my initial drive, and then I was lucky to have, being at the university where it also people working in geoscience, especially on earthquakes and seismology, and that was my first step out of physics more into the geosciences. And then over the year, a lot of, as you saw from some of the methods, the models, they're very generic mathematically, and they can apply to different things. And then this interest in other applications beyond that in neurosciences emerged, and I was lucky to connect with or make collaborators in these different areas to help on the pursuits. So just to be clear, I showed quite a few experiments. I'm not doing the experiments, right? So those are all my collaborators, and I rely on their expertise to do the experiments. But I work with the data and the modeling side with them together on those questions. So it's sometimes it's a lucky coincidence, or sometimes I reached out on purpose because I knew they were doing something what I felt was interesting from our perspective, and the collaboration started from there. I hope that's a good answer.
Thank you very much for your answer. We have a question from Patrick. You mentioned that different animals showed the same power law in their movements during foraging. Is this reflective of there being some optimal foraging strategy or method of moving while foraging?
That was originally speculated, and I showed some animals to do that, but not all. So there are quite a few animals do not share that behavior. I remember there were a very impactful Nature paper, I think in 1999, Eugene Stanley's group based on some data, but it turned out later the data had issues, and there was a revised paper about 10, 15 years later, so with different findings. So as far as we can tell now, there's some animals who do that, not all of them. It was speculated that it has to do some with optimality, but that has not been proven. If you come at it from the perspective I present today, if you look at these Paulo-like behaviors as being related to critical points, then you could interpret it that way. I mean, from the biological perspective, you could argue if the animal where is to survive, or the species, they somehow have to be optimal in some sense. But it might really depend on how you exactly define optimality in this context.
Thank you very much. We have another question from Robert. For earthquakes, is the power law distribution mainly useful for risk assessment, or could it possibly be used to predict individual earthquakes?
So, I mean, the way I presented it was basically an average or a long reporting period. And for that, it's helpful, obviously, for the hazard assessment, because then you can say every 10 years, we expect to see an earthquake of a certain size, and then you can adjust building codes. If you look at shorter timescales, I mean, people have tried that to see if there are fluctuations. So if you look more on shorter timescales, and there is some indication, maybe there are some precursors one could take advantage of. And it's also known that sometimes this slope, this B value, is a little bit different before versus after. That has been observed. But as far as I know, I don't think we have a clearly tested methodology that really reliably can use that to predict what's going to happen. That's my understanding. But I think Robert should be the expert on that.
Thank you so much. We have another question from Syed, and it's a bit of a fun one. How do you feel as a scientist when you watch a bombastic and explosive Hollywood blockbuster? For example, when they exaggerate some things to make it more appealing to be in a film.
That can be sometimes challenging. I mean, I just last weekend with my son, I finally watched Interstellar with him. He's 12, and I think that's one of the movies where they put on a lot of effort to get the physics right. But yeah, I get especially annoyed if it's like a science fiction type movie in outer space, and there's a lot of sound effects where you basically don't expect to hear anything. So yeah, sometimes I get annoyed, but I think these days a lot of movie makers trying to do a better job at getting the physics right.
Thank you so much. We have another question from Alita. What is one key takeaway or idea you hope the audience leaves with today?
Well, as I said, I hope I've convinced most of you that complex systems are interesting and they're worthwhile studying. And there's a lot of things that we need to learn about them to help to tackle some of today's challenges.
Thank you very much. I believe that's all the questions we have for today. So I want to say thank you very much, Professor Davidsen, for joining us and for sharing your research on complex systems. It was very intriguing. And thank you as well, everyone who joined us online. This wouldn't be possible without you. If you enjoyed today's lecture, we will be posting it on YouTube so you can share it and rewatch later on. And all of our previous ATCO SpaceLab Speaker Series events are also on ATCO's YouTube channel. With that, I'll send you off to enjoy the rest of your day. Thanks so much for joining us.
Thank you. Thank you, everyone.